All right, everyone. It is my pleasure to announce our next speaker for today, Filiz Dogru, who will be telling us about outer billiards. Thank you.
Thank you. Thank you for the organizer giving me this opportunity to speak in this beautiful conference. I already had listened so many beautiful, wonderful talks, and hopefully we will have more. But honestly, I should tell that I'm still not used to talk to this kind of screens. I really prefer face-to-face conferences. I'm wishing that in the future we will have that. All right, today my talk will be very, very general talk. I will talk about outer billiards and in general billiards. I will compare a little bit of old results with the very new ones in the symplectic geometry. Hopefully you will enjoy it. Let's start. Let me start with the billiards. Billiard type of dynamical system is around a long, long time since Birkhoff. And I will give brief history of the only outer billiards in a minute, but please let me start with the definition of the usual billiards because everything starts with that. A mathematical billiard consists of a domain in the plane and the mass point inside the domain. This mass point moves inside the domain along the geodesics until it hits the boundary. The reflection of the boundary is elastic and subject to a well-known geometrical law, which is the angle of incidence equal to angle of reflection. After the reflection, the point continues on the free motion on the geodesic line, and it continues until it hits the boundary again. This also known as a law of geometric optics. Billiard table, which we domain that we call it a billiard table, can be also a polygons. If you look at here, in the polygons, the definition is exactly the same, but at the same time, if the point hits the corner of the polygon, then further motion is not defined. Well, now I will carry the billiard game outside the table. Outer billiards, and also it's well known as a dual billiards in the old days. It's changed. I will tell you why we call it the dual in the old time, but right this moment, I think everybody is using outer billiards and I follow that trend. This type of billiard, it's outer counterpart of the usual billiard map. It is also known dual billiard, as I said. And this is a compact, convex, plane domain. It's a billiard table. Let's call it P, and the curve is, a boundary curve is delta. And then the map is defined outside of the domain to itself. Let me give the definition briefly. When we have a point on the outside the table, we can have two support line or tangent line from this point to the curve. One of them is this one and the other one is this one. When we have this curve, boundary curve oriented, I am going to pick this one as a tangent line. And the other one will be the inverse of the map actually. Well, when we have this tangent line, we are reflecting the point at the tangency point to get the image point. And motion will continue exactly the same way. And whenever the orbit goes to the original point, then we will have a periodic orbit. This is very well known. It's area preserving, very nice map, in fact. And we can define the same map on a polygonal table also. But in this time, when we have this extension of the sides, when we pick the points from there, there is no place to reflect. So in that case, functions are not, the function is not defined, map is not defined on those singular points. Well, let me give you a little bit of history. First, polygons circumscribed about closed convex curves appeared in M. Day's paper in 1945, which this is the shape that they used in the paper, in fact. Later on, this is, I heard, but I never seen it. Newman had in the late 50s an entertainment paper sharing ham and eggs and mentioned about this type of polygons. But Moser popularized this map, realized it very important map, and popularized it in the 1970s. And this, he used this map as a crude model of planetary motion in his paper. Actually, this picture is directly from his paper. Today, the subject is still very popular in mathematics, physics, and mechanics. The main idea for the outer billiards, the main question is, if the orbits going to infinity, escape to infinity, or in other words, can we find unbounded orbits? Well, several mathematicians found several different answers for certain polygons. For example, those first three of them had polygons with rational vertices, regular polygons, and more generally quasi-rational polygons. And in this case, all the orbits were periodic. So they are periodic, that means they are bounded to. The first unbounded orbit found in 1992 for the Pentagon. Sorry, it's not unbounded, infinitely many. They are all periodic up to this point, but right now it's the orbit is infinitely many. It's not periodic at all. But the thing is, still it's bounded. So still we didn't know whether the orbit's escaping infinity or not. We carried this problem on the hyperbolic plane, and we found that there are certain, I will talk about this one a little bit more in a second. We have some certain polygons that orbits are unbounded, escaping to infinity. Finally, in 2007, Schwartz found one particular polygon, which is a Penrose tiling polygon, and Penrose kite, that he found also unbounded orbit in Euclidean plane. But the proof is so complicated and computer-based that it's numerically proved. So honestly, it's very hard for me to understand. But let me talk about just a little bit of an hyperbolic plane. I believe all of us know that hyperbolic plane has different models. In this study, I worked on Klein model and Poincaré model. Both of them has some advantages and disadvantages to work with it. For example, Klein model is very easy to draw the pictures. You will see lots of pictures in the Klein model, but the thing is, angles are distorted. And on the Poincaré model, we have the angles are fine, but the length and distance are, I mean, the arcs, geodesics are arcs, not as straight lines. It's pretty difficult to draw it by hand. But anyway, I use both of them whenever it's easy to use. So in the hyperbolic plane, outer billiards are defined exactly what we have done in the Euclidean plane. We have a polygon, we have a point outside, inside the, of course, plane, hyperbolic plane. And then we moved, clearly I used a Klein model in this picture. We used the tangency point as a reflection point, and then we will be able to define the map in here. In this hyperbolic plane, the regular right angle gons are very important. Let me give you as an example. This is definitely a Poincaré model. we have a pentagon in here, and it tiles the whole hyperbolic plane. If I consider the middle tile in the here, center tile that we can see is the billiard table, then we will be able to find all the orbits are periodic. And periodicity is also related to the n-gon. Okay, now let me give you a couple more examples. Again, using the Klein models, we will be able to find for some tables, some polygonal tables, some orbits are at the infinity, which is unbounded, but they are finite. And the most important one is, under certain circumstances and some certain polygons in the hyperbolic plane, every single orbit escaped to infinity. There is no periodic orbit inside the plane, but you may find it at the infinity. So these are unbounded orbits. And the last one is completely random. You have a table, random polygonal table right here, and we can see that pack of periodic orbits are right here, and one, and right here is another one, and some of them is infinitely many, and then there is no periodic orbit in that sense if I pick some points. And then also I can see some kind of clusters here that they can create periodic orbit at the infinity. Actually, I would like to talk about today a little bit more in the new billiard type, which is in the symplectic geometry. But before talking anything about the spherical geometry, that's not right. That's not fair to go further. So let me say a couple of words in the spherical geometry. I think main idea in the spherical geometry that all of us know, the duality between the great circles and the poles. Well, great circles is oriented, and then poles are picked after that. An angle in this geometry translated to area by the Gauss-Bonnet theorem, which links the differential geometry with the topology. It connects the curvature of surface from a geometry to its Euler characteristics from topology. Therefore, angles between the great circles are equal to spherical distance of the poles. They are poles. And that translates in the billiard world is inner billiard and outer billiard actually dual to each other. So duality actually comes from here. But I'm not getting into too much detail in the spherical geometry. I prefer to go the new results, which is in symplectic world. Let me go there. Since the symplectic geometry is actually more recent than the other geometries, let me give you a little bit of introduction for that. Symplectic geometry actually is a branch of a differential geometry that studies symplectic manifold with a symplectic structure we call form. Can be put on even dimensional space. Actually, it's topological in nature as well as geometric, because although all its concepts are initially expressed in smooth, for example, in terms of differential forms, they do not involve derivatives. If we compare symplectic geometry and the Euclidean geometry, we can see very nice similarities and differences. In Euclidean geometry, we work on lines, angles, planes, circles, and distance measures. And we do this kind of measurements, especially distance measurements, and the structure on the Euclidean geometry is dot product. Well, geometry basically is the study of the structure of spaces, right? So in that case, we have a dot product here. And dot product is a symmetric operation. In symplectic structure, when we talk about in the symplectic geometry, formally is a closed non-degenerate two form. But briefly, is a geometrical object allows us to measure of size of two-dimensional objects in symplectic spaces. Well, in the symplectic geometry, we have dot product in the Euclidean geometry. In symplectic geometry, we have forms, two forms, and they are anti-symmetric. This is the difference. When we have anti-symmetric forms, we have omega, let's call it omega 0, and the operation on the vector by itself will give us 0. And therefore, because of this, no analogy of length, but there is notion of signed area in 2 dimensions. So that's why I give the brief definition of the symplectic structure. At the same time, omega 0, the form, is non-degenerate. So that means for all the non-zero vectors, at least we have another vector that we will be able to find non-zero form. And then we also have another property is closed, that omega 0 is closed, which is the derivative of it is 0. Let me explain just a little bit of it. What does that mean? If it is closed by the Stokes theorem, the area of a surface, if we have a surface fixed boundary, and if we change the surface without changing the boundary, the area won't change. And this is actually uses the Stokes theorem. Just to see what kind of a structure is this in a simple way, just think about R2. And we have in R2, if we defined omega 0, 2 form as a determinant of 2 vectors, it's just the area of between these 2 vectors. That's this parallelogram. Actually, this geometry is pretty strange for me. So that's why I will give you one more example just to show the how strange geometry is this. On R4 is the example is, if we have a surface, the symplectic structure defined as the sum of area forms in the first in R2, first in R2, and the total is R4. And then if you look at carefully, the location of the surface, if you locate and orient it and rotate a little bit, you will be able to find, even though your surface is like surface, you will be able to find 0 area. It's pretty strange for me. Okay, the most recent things actually, the billiards moved into this kind of geometry, and symplectic billiards are defined. So let's see. Symplectic billiards are very well in mathematics. First of all, in mathematics, some systems call a billiard, but they are actually not traditional billiards. They are motivated by it. Here's an example is symplectic billiards. The name is given symplectic because they can be defined in linear symplectic spaces. In the plane, symplectic billiards commute with the affine transformations. Let's see. How do we define this symplectic billiards? Well, you have a translation of or reflection of oriented chord to another oriented chord. And reflection law is given right here, which is xy is reflected to yz as long as you have xz is parallel to the tangent line at y. Well, this reflection law can be used, can change the variational formulation. And actually this is very nice because in this particular paper, there's one very nice explanation with all 3 billiard types using variational formulation and its relations. What is the formulation of the symplectic billiard first? Well, if you fixed x and y, then y is located such that this triangle has the extremal area. And then we will find similar variational formulations for the other type of billiards. So let me go and explain that one. The first picture you are seeing is inner billiard, and the second picture is outer billiard, and the third one is symplectic billiard. The first one, if you remember in the beginning of the talk, these two angles has to be equal, so that was the reflection at the boundary. But right now, let's think about this way. If x and z are fixed, then y location determined by the length, total length of these two geodesics is extremal. In this case is maximum. And for the outer billiards, we can think about this motion continuously. And if we have a periodic orbit, that means we create a polygon which circumscribes the whole billiard table. And that polygon has also extremal area. Similarly, we have just a second ago, we talked, if we fixed x and z, and then location of y in such a way that we have this triangle has extremal area. This is a very good comparison between these three billiard types. Let me give you a couple of recent results in the symplectic billiards. We have time, right? So, yeah. Let me see. If we have a billiard curve is smooth, strictly convex, closed, and oriented. In this case, if you look at a point in X somewhere, and then we have another point, X star, which parallel tangent lines. Phase space for this system consists of pair of points like X and Y, so that by the orientation, this Y is between this X and Y. Clearly, this system has invariant curve. A chord X to X star will be reflecting to X star to X itself. So this is the two periodic orbit, and it's true for all the X points on the boundary. Of course, this is being strictly convex plays a big role in here. There is one important theorem that due to Alberts and Tabashnikov, it says if the curvature of the boundary curve vanishes at some point, then the symplectic billiard in the curve has no caustics. In other words, invariant curve. So we have actually similar results earlier, but for the outer billiards due to Gutkin and Katak, it says if the radius of curvature vanishes at some point, then no invariant curve outside of the table. There are a couple more nice results. We can have symplectic billiard table, maybe a polygon, considering only convex polygons, of course. And if in this case, actually, the symplectic billiard is not defined if the head of an oriented chord is a vertex of the polygon, or when the head and tail of an oriented chord belong to a parallel side. In this situation, if we have irregular polygons and trapezoids in the symplectic billiards, all billiard orbits are periodics. We have another symplectic billiards actually in spherical and hyperbolic geometries too, but I don't know much about those, and I will stop right here. Thank you for listening. These are the references, and if you would like to, if you are interested in, I have a long list of references, so I can give it to you. Just let me know. Thank you.
Wonderful. Let's thank our speaker. Excellent. And I think we might have time for a few questions. If anyone has a question, please ask or put it in the chat.
So I'm just curious about, like, in general, like what type of stuff the field tends to ask. So like, just like funny enough, I guess this is just what happens when you're, you know, in the 2000s. I just finished undergrad. And so like the only dynamical systems I've seen have been like differential equations, like applied to biology. But yeah, I've seen this before about like the billiards being like a classic dynamical system that's like 100 years old. So I guess I'm curious about like where like the things, like kind of, I guess just like what type of questions people tend to ask next about these type of things.
Orbits, usually they are trying to, I mean, there are so many open questions actually here, especially polygonal billiards. They are a little bit more interesting because of the discontinuity points. Orbits are very important. I mean, do we have what kind of polygons gives us like infinite orbits? What kind of polygons will give us bounded orbits, periodic orbits? What is the periodicity, how it's related? So there are so many works, and at the same time so many open questions. I mean, if you want this, particularly the first paper in the references, they have a lot of open questions.
Cool, thank you.
Thank you.
I had a question. You had mentioned you were going to connect the term outer with dual, and did you do that and I missed it, or?
Oh yeah, it was in the spherical geometry. So let me go back in that slides one more time. Sorry, where is it? Oh, right here. Okay. Okay. In the spherical geometry, this, since we have the angles, great circles, and distance between their poles are equivalent, and also we have by the Gauss-Bonnet theorem, and then you have the equivalency of inner billiards and outer billiards, and in that case they use this equivalencies as a dual. They said, oh, dual each other, so if you do anything in the inner billiards, they will be able to do the same thing, just changing the angles and distances, and then do everything is the same. So that's why they call each other a dual. So outer billiards called the dual billiards in the beginning when they start studying, but later on the outer name came out more and everybody start using the outer, so I just follow the trend.
So is there any relationship between inner billiards and outer billiards in the Euclidean case?
Well, no, the outer billiards is the outer counterpart of the interior billiards. And its definition is a little different. I hope it answered the question.
Yeah.
Thank you.
All right, let's thank our speaker again and get ready for our next speaker here in about a minute.
Thank you.